Hey everyone, Lewis here from Easy2 Digital, where we help you reclaim your time and upgrade your lifestyle. Today, we're diving deep into a groundbreaking AI innovation that's set to redefine how we train massive large language models. Imagine a world where hardware failures don't halt progress, where global compute power can be harnessed seamlessly, and where the cost of developing cutting-edge AI plummets. This isn't science fiction, it's the reality Decoupled DiLoCo promises. We're going to break down this game-changing framework from Google DeepMind and Google Research. Stick around as we explore Chapter 1, the looming crisis in large model training, Chapter 2, why traditional methods are failing us, Chapter 3, Decoupled DiLoCo, the architecture that changes everything, Chapter 4, the engineering brilliance behind the breakthrough, Chapter 5, unlocking global compute performance and adaptability, Chapter 6, the bandwidth revolution and your AI future. Trust me, you won't want to miss this. Before the show starts, remember to subscribe to our channel, give it a like, and share today's content. Thank you all for your support. Alright, let's talk about the elephant in the room: training colossal AI models. Just a year ago, we discussed Google's original DiLoCo framework. Now, Google DeepMind and Google Research have dropped a bombshell with Decoupled DiLoCo. What's the big deal, you ask? Well, this isn't just another paper, it's led by Google's chief scientist, Jeff Dean himself, and it directly tackles the Achilles heel of large-scale AI pre-training. We're talking about a future where hardware failures, which become daily occurrences with millions of chips, no longer bring everything to a grinding halt. Traditional synchronous training wastes an insane amount of compute power. Imagine this: when you scale up to 2.4 million chips, conventional elastic data parallelism only uses about 40% of its potential. The other 60%? Gone. Just waiting for repairs and reconfigurations. But Decoupled DiLoCo? It promises a staggering 86% effective throughput even in these extreme, failure-prone environments, virtually eliminating downtime. And get this, its communication bandwidth demand is a mere 1/60th of traditional methods. It could even integrate old chips and scattered compute power from around the globe into a single training run, without sacrificing model quality. This is huge, and it's time to break it down. So, why does pre-training huge models get less efficient as they get bigger? It all boils down to the industry standard single program, multiple data, or SPMD. Whether it's data parallelism, tensor parallelism, or sequence parallelism, all mainstream LLM training frameworks strictly adhere to SPMD. This means all accelerators must march in lockstep, completing a global synchronization at every single training step. Think of it like in an assembly line: if one workstation hiccups, the entire line grinds to a halt. But when you scale to hundreds of thousands, or even millions of chips, probability becomes your worst enemy. The paper throws out a startling number: if a single chip has a mean time between incidents, or MTBI, of 1 year, which is already top-tier industrial reliability. A cluster of 2.4 million chips will have a mean time between failures, MTBF, of less than 1 minute. That means a hardware failure every minute. Traditional training simply can't keep up. Decoupled DiLoCo isn't just an improvement, it's a revolution in philosophy. Imagine the CAP theorem applied to LLM training: consistency, availability, partition tolerance. Traditional SPMD prioritizes consistency above all, demanding perfectly synchronized model parameters across all devices, sacrificing availability and partition tolerance. Decoupled DiLoCo flips this on its head. It puts availability and partition tolerance first, tolerating limited parameter inconsistency without sacrificing model quality. This means training can run continuously, even amidst faults, latency, and mixed hardware environments. But how? It builds on the DiLoCo lineage, which started with Arthur Douillard's team in 2024, shifting from global syncs to less frequent ones, and then streaming DiLoCo in 2025, which asynchronously streamed parameter fragments. However, these still locked all learners into step. Decoupled DiLoCo, leveraging Google's Pathways philosophy, takes this to the next level: completely asynchronous decoupling. It breaks the synchronized shackles by splitting the integrated SPMD cluster into two main parts: independent asynchronous learners and a central syncer. They operate completely decoupled, confining failure radius to individual learners. This is truly groundbreaking. Let's get into the nitty-gritty of how this magic works. The learners are the foundation, operating entirely independently. Each learner holds a full model replica, processes its own data, and runs its own inner optimizer. critically, they don't wait for anyone. They do three things: execute local training, asynchronously send parameter fragments and metadata to the sinker in the background without interrupting local training, and listen for update instructions from the sinker. If a learner fails, other learners don't even notice, they just keep chugging along. This is like turning one massive exam hall into many independent smaller ones. If one room has an issue, the others keep taking the test. The sinker, running on stable CPU resources, is the brain, aggregating and updating global parameters. Unlike traditional parameter servers that wait for everyone, the sinker uses three core mechanisms: minimum quorum aggregation, needing only a predefined number of learners to report; adaptive grace window, waiting briefly to incorporate more updates without slowing down; and dynamic token-weighted merging, where updates are weighted by the amount of tokens processed, ensuring fairness. Plus, an algorithm called radial directional averaging, or RDA, ensures gradient norms don't decay with more learners, enhancing stability. Engineering brilliance, I tell you. Beyond these core mechanisms, Decoupled DiLoCo includes two major optimizations addressing communication and deployment. First, balanced tensor fragmentation. Instead of traditional layer-by-layer or uneven tensor fragmentation, it uses a greedy bin-packing algorithm to evenly distribute all model tensors into 24 fragments. Only one fragment is transmitted per step, ensuring continuous communication while minimizing peak bandwidth. Second, outer gradient compression, compressing 16-bit BF16 gradients to 4-bit int4 results in almost no performance loss, cutting bandwidth by another 75%. This is monumental for cross-regional training in low-bandwidth networks. To prove its resilience, the team used chaos engineering, a first for LLM training validation. They simulated 5 core failure scenarios, replicating a million-chip environment. The results were clear as chip count grew to 2.4 million, traditional methods tanked, but Decoupled DiLoCo's effective throughput increased, hitting 86% with 16 learners, with nearly 100% uptime. It's truly zero global downtime. But here's the real kicker: it handles heterogeneous hardware flawlessly. Mixing TPU-v5e and TPU-v5p chips with significant speed differences, the system maintained 100% compute utilization and identical model performance. Old chips, new chips, all working together. And compute scavenging. It lets new learners asynchronously pull model states from neighbors without blocking training. Experiments show adding temporary compute slashes training times. Imagine consolidating idle compute power globally. This isn't just about efficiency, it's about democratizing access to massive AI training. This bandwidth revolution is perhaps Decoupled DiLoCo's most transformative feature. For a 5B parameter model, a 1-second compute step, and 2 data centers, traditional data parallelism needs 104 gigabytes per second of bandwidth for 90% utilization. Decoupled DiLoCo? A mere 1.7 gigabytes per second. With 4-bit compression, it drops to 0.43 gigabytes per second. We're talking 2 orders of magnitude less bandwidth. In an 8 data center, cross-regional scenario, the gap widens further. They even tested it across 4 US regions. Non-collocated Decoupled DiLoCo training was almost as fast as same-city clusters, while traditional methods slowed by 10 to 20 times, making them unviable. This isn't just a technical paper, it's a paradigm shift. It completely overhauls the SPMD paradigm that has dominated LLM training for over a decade, moving from consistency first to availability first. Jeff Dean himself noted that he proposed asynchronous distributed training 14 years ago, but the technology wasn't ready. Now, Decoupled DiLoCo makes it a practical, industrial-grade solution. As LLM pre-training expands to cross-regional clusters, mixed hardware, and fragmented compute, the constraints of bandwidth and hardware reliability will only grow. Decoupled DiLoCo isn't just an advantage, it's becoming a necessity. This breaks the scaling bottleneck for AI, drastically cutting the cost of training trillion parameter models and opening doors for more institutions and teams to participate in cutting-edge AI development. This is the future of AI, and it's happening now. Don't be left behind.